have Maryanne Wachter, who is going to talk about Cython in practice, a deep dive into legacy C integration and debugging. So please make her feel welcome.
Thanks everybody for joining in this first post-lunch session on a Saturday. So I'm going to talk about how you can use Cython with old C code and make it accessible in Python. So in terms of the motivation for how I got into this as a project, a little bit about me. My background is in structural engineering, but I've moved into pure software engineering in the last couple of years, and I've been using Python for that since 2015. So let's see if my video is going to play. Nope. A couple of years ago, I presented at a PyCon about a project that I built with Cython that was for architectural constraint solving. And so this project was a greenfield that I wrote in Cython. I wrote a minor amount of C++, and then I rewrote an algorithm for generating form-found surfaces based on boundary conditions. So based on that talk, I was actually contacted by a maintainer of a package called Section Properties that's on PyPI. And so this is a library that structural engineers can use, but it has a couple of dependencies, including a triangulation library that's needed to discretize sections to allow users to generate a mesh that you can use for finite element analysis. So what's the underlying library that Section Properties is using? It's called Triangle. It's C code. It was published in the early 2000s. It's actually extremely well documented for academic code. It was written by Jonathan Shuchuk, who's a professor at Berkeley. So Triangle is actually used in many geometry libraries across languages. Like there's a Rust implementation, and there are other wrappers in other languages. And the main thing about Triangle is that it produces triangular meshes without small angles, so you won't have a very acute triangle, which is what you want for finite element analysis. And so what finite element analysis is, it's a lot of what I did as a structural engineer, and this is actually what got me into software, was writing subroutines for FEA. And basically, FEA is a method for discretizing surfaces or solids that allows you to determine forces and stresses to generate contour plots like these that say how close you are to structural failure. So there is a PyPI package for Triangle. It's maintained by one person. They aren't very responsive to user requests. The maintainers on Section Properties had reached out to them a couple of times. And the issue that they had was that it wasn't built against all the architecture that they wanted, and it wasn't built against all the Python versions that they wanted, and they were kind of at the mercy of this maintainer who doesn't really need to maintain it, so they just wanted more control over it. So the goals of the project was to write a new wrapper. We decided to make it object-oriented to possibly extend some of the functionality. Needed to work on Python 3.1 and above. It needed to build on all architectures. So I believe the issue was that Intel Macs and Silicon Macs were never supported under Triangle. And also, the goal of the project was for me to be able to pass on some of the work to the other Section Properties maintainers so that there wasn't a single point of failure. So in terms of an overview of Cython, if you're joining, I hope you know a little bit about Cython. But Cython at a glance, it's an optimizing static compiler. It's a superset of the Python language. You'll get to see language examples in further slides. And it produces C files and extensions and executables. And you can take advantage of C performance, so the speed, optimization, releasing the GIL. So I previously had written in Cython just to be able to gain the performance, but this was an example of using Cython to make something accessible that wouldn't be otherwise. So when it comes to what are the conventions of Cython, you have a couple of additional file extensions. You don't just have .py files. So .pyx file, this is only required if you're going to make a function declaration that's a CDEF. A .pxd file that is similar to a header file in C or C++, and .pxi files, this is like an include file. It's not really necessary anymore because you can use C import to import your functions into a .pyx file. So in terms of the type declarations, there are two additional function type declarations. There's CDEF, and that is what you would apply to a Python function if you only want it accessible from other C classes or objects. CPDEF tells the Cython compiler to make that method accessible in both C and Python. There are memory views, which are stand-in for arrays. The import statements, when you are importing into a .py file or another .pyx file from a .pyx file, you need to use a C import rather than just an import. And then when you are working with like a pure C function, that CDEF signature, you need to include the type that's going to be returned from it. And in general, you should use static typing where possible. So what does this integration look like for mapping directly from a C library into Cython? So the left-hand side is a triangle.h file, and so that's what I had from the triangle library, and ctriangle.pxd was the header file that I made to mirror it. So you do need to concern yourself with pointers when you're working with Cython, so that's what those asterisk characters represent, is a pointer to a struct. So I went from a struct in triangulate.io to a CDEF struct. Reals are mapped to doubles, ints are mapped to ints, and then you can see that you've got a struct triangulate.io, but I could just declare that as a triangulate.io within the function signature. So triangulate is the magic method that does everything, so I needed to have an interface in my Python and Cython code that would basically call the C, or mirror the C program. So there are a couple of additions to Cython classes. So if you are doing like a CDEF class, you have this cinit method, the dalloc method, and then I also had a lot of sort of bookkeeping methods for setting properties and retrieving them. So mapping them from the C struct into a Python object. So cinit is the C-level initialization. It's guaranteed to be called when the object is allocated, but before it's fully initialized. So it gets called before init. And it's where you're supposed to do like the safety C-level initialization, so the owned data structures. In this case, the IO attribute needed to be initialized with a null pointer, which I then set once I actually had an input file. So the counterpart to cinit is anything that you need to allocate needs to be deallocated at the end. So you end up, in my case, with a bunch of if statements for basically saying, if this has been set, make sure that you free it at the end, and then in the end, it deallocates self.io itself. In terms of the data structure for this problem, you have points, which have an x and a y coordinate, because this is only working in 2D. You have point labels that are mapped to a point list, and then the triangles are defined by 3 ordered points. In terms of using those properties, setters and getters, so this is an example of a property that iterates over the C struct to populate it to a Python list once you're done with the analysis. And then in terms of the actual setter, this is where you need to use a contiguous array from NumPy, which is what is going to be expected from the C code. And then memory allocation is based on the size and value type iteration. So there's an iteration over the input to place vertices into the struct for the C program. So last piece is the actual method that does the magic. So it needs to work with 3 separate instances of a triangle object because that's what the method in the C code expects. So it expects an input, it expects an output, and then depending on if you've set an additional flag, it'll also do like a Voronoi output for you. There's also a whole bunch of flags that you can set that control what the output is, how discretized the mesh is. So those are important because they led to some interesting problems later on. So I wrapped the library. Didn't take that much code, it was like less than 1,000 lines. And then I went to writing my tests, and the first thing that happened was all of my tests passed for in CI when I was running against Mac and Ubuntu, but then in Windows, I got a Windows fatal exception. And this code corresponds to a memory corruption, and it was not consistently reproducible. Sometimes all of the tests would pass, but quite often some would pass, some wouldn't. It was not test dependent, but yeah, it had to do with memory corruption. So that's when I got into debugging. So what does debugging look like for a Cython project? There's 2 kinds of debugging you can do. You can do runtime debugging with CyGDB, and the nice thing about CyGDB is it lets you set breakpoints within PyX files. You can step through your Cython code line by line. You can inspect Python objects and C variables. It utilizes GNU GDB as an extension, so it's got similar syntax, and it really allows you to understand program flow. There are some drawbacks to this method. It's a bit fiddly to set up, which Cython cites directly. It's a general purpose debugger. So in my case, I already knew that I had a memory corruption error, so there's no memory analysis, or at least not to the extent that I needed it. So it can't detect memory leaks, it can't detect buffer overflows, use after free errors, or memory usage. So you kind of need to know ahead of time where the potential problems exist. Like this would be a better debugger if I knew that there was one specific test that was failing each time, then I could probably use it, but in this case, it wasn't so helpful. But if you do want to configure CyGDB, you can just set it up within your build.ext file or your setup.py file. It's just a flag to pass that will add additional directives to the C code that's generated. And then you'll probably want to use like multiple windows or like a terminal manager like Tmux in order to basically run the debugger in one window and then the other window actually run the program, because you have to have it actively running, and then you can do it through a configuration file, but you can actively set basic commands like setting up a breakpoint for a specific class name and a method name. I found that when debugging, especially choosing debugger tools, it's best to use the tool in the context that it was originally written for, so which architecture it was written for. So I ended up actually using Ubuntu for all of my debugging purposes. So even though I work with a Mac, I used like a minimal Docker file to be able to install the debugger and try this out. And so one of the things that's a little bit different is that you might need to make some changes to like the security within the Docker debugger the Docker container, because you are going to be basically testing with some guardrails off. So yeah, the best way to figure out what my particular error was to use a memory profiler like Valgrind. So I'm actually only going to be talking about a small subset of what Valgrind can do. But originally, because the problem had originated in Windows, I wanted to try this on Windows. But the problem was the address sanitizer does not work with Windows because it's not supported in Windows 11. I checked this morning, that's still the case. Also, I'm an Emacs user, so I didn't want to go through the headache of setting up all of the Visual Studio code and configuration to do this kind of debugging. I also didn't use OS X just because of the potential headaches with system integrity protection. Clang CL is, I kept having issues with it pointing to the wrong target. I tried building a couple times. It was pretty fiddly just because I was sort of working outside the Windows ecosystem. So yeah, I landed on Valgrind just because it had very clear documentation and it was easy to set up. So what do I mean when I say there's a memory corruption issue? So that can be accessing memory outside of allocated bounds, using pointers incorrectly, double freeing memory, using memory after it's been freed, buffer overflows, or platform-specific data type representation. And in my case, I hit 3 of these. So the first issue that I had, which goes back to the Windows, it only happening on Windows, was that I was pretty sure that the original C code should work. So I was trying to preserve it. And it turned out there was an underlying data type compatibility issue. I wrote a little script to actually test in GitHub what was happening with the test runners. And this is where I discovered that anywhere that I had an unsigned long, it was only 4 bytes instead of 8. So I had to edit the underlying C code and make a macro to make this work. So yeah, the lesson learned from this, it's probably okay to modify the original source code, especially if it was written more than 20 years ago. So I changed it from an unsigned long to an unsigned long. So yeah, Valgrind configuration, pretty easy to set up, just one install command and then a couple of flags to set, basically to say where am I going to store this and what am I running. And once I ran Valgrind and I generated the log file, I got a bunch of lines that looked like this. Some said invalid read, some said invalid write. They had a size of 8. But in terms of what this line means, so the first segment with the number in it, that's the process ID. This indicates, based on Cython's name mangling, that this is a Python wrapper function. This is the Python module, so it's being accessed through scitriangle.io. This is the class within that module. And this is the Python method index, so that's what the 25 is, and the name of the method that is causing problems. So in this case, it was my fault. When I was setting, using those setter functions that I mentioned previously, I wasn't allocating enough space for the holes, so when Triangulate was trying to access the holes, it was reading the wrong part. So that was a pretty easy fix. But then I ran into this other issue where Valgrind was telling me that I was double freeing memory. And if you remember back to the deallocation, that was it was a pretty straightforward thing to set up. It was like, just check if this exists and it's not null, then free that memory. And I was doing that for each struct, so how could that be duplicated across instances? And so where I was seeing this double free memory was for 2 methods, or 2 attributes. One was the holes and one was the regions. So the way that Triangle defines a hole is you need to have a closed polygon, and then you put a point within that to specify that it's a hole. Regions allow you to specify like a finer mesh in certain areas, so it's just another way of basically specifying different pieces of your discretization. So as I mentioned before, there are a bunch of different flags that you can set in Triangle. It's also not necessarily clear from the documentation how they interact and which ones you can use with other ones. It's a little bit of a challenge. So I had originally, in my test suite, been running it with these flags, and I noticed that section properties was running it with this other set of flags. I was seeing the free memory error when I ran it against the section properties test suite. And that was because the specific flags that I was setting, so this is like the documentation within Triangle of what each one means, there was a macro that was being triggered by adding the P flag, and it was for writing polygons to the output. And the problem is, it says that if there is a polygon flag set, it's just using the same reference for the input struct and the output struct. So at the end, when I was freeing memory from the input struct, it was already gone by the time the output struct was being deallocated. So to fix this, again, I edited the underlying C code just to copy that information because it's the same from the input to the output. So now I finally had fully building, working against all the tests, and I moved into packaging, which is everyone's favorite thing in Python. So I originally did all the packaging with poetry. So I chose the core build backend, and there were a couple of other flags I needed to set. So I mentioned poetry, when you're working with Cython, you can use a build.ext file, and it will generate your setup.py file, so you can then commit that to your repo. In terms of the CI, this is what was required, this is what was asked for. So running against all these versions of Python, it starts at 3.10 because of the changes to NumPy. So we're using NumPy version greater than 2. And then for the OS, it was required to work on Ubuntu, Mac, Windows, and Intel Macs. So the jobs that I set up were pretty standard and basic. I used Twine for publishing to PyPI. That was pretty straightforward. I went through the process of trying to redo this in UV because I am using UV for all of my other projects currently. And that was pretty straightforward to set up in terms of what files I needed to use. So I just changed from using build.ext.py to a setup.py file. And then within UV, that simplified what my PyProject.toml is. I do have other directives in here, but they're just not relevant to UV specifically. But the problem that I ran into is that with UV CI, the setup tools backend builds this platform tag just for the Linux x86-64 architecture. And what PyPI expects you to have is the many Linux build. So when I did a little bit of digging, right now UV does support build at backends for extension modules. If you're writing something in Rust, you can use Maturin. But if you're using C, C++, Fortran, or Cython, you should use scikit build core. But if I use scikit build core, it's going to require me to do a bunch of CMake list configuration. And it looks like right now it's not super well documented or supported because this is directly from their documentation. It doesn't include helpers for F2Py or Cython yet, maybe eventually. But I can still use UV in my CI step. So the workaround is to build wheels with CI build wheels, which will make those many Linux wheels. And I can still run my tests with UV run PyTest, and then I can use UV publish as the final task. And since I'm using GitHub Actions for this, I can just add a trusted publisher to the project so I don't have to set any variables. So the takeaways from working on this project, when you're working with legacy code, you should review some of the conventions for different architectures because it might lead to some interesting results. You should simplify your debugging environment as much as possible. I found Valgrind was the lowest barrier to memory troubleshooting. I probably could have written better tests and flagged some of this earlier on, but that was a lesson learned. Another thing that was a big takeaway from this is to give more talks. I wouldn't have gotten to work on this if I hadn't given a previous PyCon talk that someone saw. And this is the kind of stuff that I really like working on because it gave me the opportunity to support an open source project and also do some low-level work that I don't necessarily get to do in my day job. And so with that, yeah, I want to thank you all for coming to my talk. I gave a different version of this at PyCon Japan. I highly recommend trying to present at other PyCon conferences. And yeah, also thank you to Connor, Robbie, Martin, and Nathan, who have either submitted PRs against this or helped me with some of the debugging problems.
So if anyone has any questions, we have microphones on either side of the camera there, in this column and this column.
Hi. So we've used Cython at our company a bunch, and I feel like had very similar problems. And some of the complaints we got were like, it's so hard to debug. And so I was kind of wondering, you used Docker Compose and you set up the debugger. Like, what were the main benefits you saw from that? I guess, like, yeah, how much time did you have to learn how to set that all up? And what, because, like,
Yeah.
I would love to set that up and use that.
Yeah, I use Docker a lot, so that was helpful. I mean, I do have a Linux machine, so I could at least like test it initially. But yeah, once I like kind of wanted to have the similar workflow, for me that just made the most sense because I was like, the debugger was written for this architecture, I should take advantage of it.
Gotcha.
Yeah.
Sweet. Well, thank you.
Yeah.
Yeah, so the double free issue you had, you fixed it by removing pointer aliasing from the underlying C library.
Yeah.
Like, was that there like as a performance optimization, or was it just a bug in the C library?
It was, I wouldn't even call it a bug necessarily because it's just like how I was using it versus how the original code was using it. There was no optimization. It was basically just copying, instead of having the same reference, just copying it from one to the other. Yeah.
Any other questions?
So is there a newer Python version you recommend to use with Cython?
I think it works with anything that's above 310. I actually, don't quote me on this. The reason why we're supporting 310 and more is because of NumPy. It's not because of Cython. Cython has had like a significant version change in the last like 2 years. It went from being like a 0.29 build to like 3, and right now it's at 310. Sorry, like the version is 310, not that it's Python 310. But yeah, I don't remember off the top of my head which versions of Python Cython is currently supporting. But I do know, I have seen in the compiled code, if you're building against 3.13, you'll start to see like free threaded directives in there as well.